Hello everyone, my today's topic is limit and smoothness of a function. Now before going to limit and smoothness of a function, let us define few basic terms. Function. Now let us define a function. I'll define a function on two sets x and y. So the definition of function is a rule or mapping in which every element of x assigns to unique value of y, or the unique element of y is called a function. So now what I am trying to say over here is the set x and y are two non-empty sets in which I'll be assigning the values of x to a unique element of y. So the elements will not be repeated when I map these two. Now if I just represent this, now 1 is mapped to map, so 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3 and 4 is mapped to 4. You can see that none of the elements of x are marked to the other elements of y, so that the element of y is having two pre-images. Suppose if I mark 1 to 2, then obviously it is not a single pre-image on x. So now let us know the other terms. For example, domain, codomain and range. So now I'll define a function f of x as x square, and f maps from natural numbers to real numbers. So now if I have to represent this, I'll take the values as 1, 4, 9 and 16. The reason is I have defined the function as x square. So 1 is obviously mapped to 1. F of 1 is equal to 1 square, that is 1. So if I put f of 2, then I'll get 4. So 2 is mapped to 4, 3 is mapped to 9 and 4 is mapped to 16. Obviously there are many elements in between. So this is my natural number set and this is my real number set. My natural numbers are called as domain. If I take f of x, then the values that I represent in x are the domain. Real numbers are my codomain. F of x is equal to x square. I'll take this to represent my codomain. Now coming to range. Now range, I'll define range of f as f is equal to f of x such that x belongs to x. Now range is a subset of codomain. So now let us see what is the limit of a function. I'll take a function f of x, then I can define limit of x at a point a by limit x tends to a f of x. In limit, there are two types of limits. Left hand limit, or it is also called as LHL, and the second limit is right hand limit, or RHL. So now left hand limit, I'll define a function f of x and I'll take the left hand limit as limit x tends to a minus f of x is equal to limit x tends to a minus f of a minus h. Now we have already studied it that left hand side will always have a minus sign. So I have taken it as a minus just to represent that it is the left hand limit, and I have written it as limit x tends to a minus f of x is equal to limit x tends to a minus f of a minus h. Similarly, if I define RHL on f of x, then I will get limit x tends to a plus f of x is equal to limit x tends to a plus f of a plus h. Now let us see some examples on it. I have taken the first example. If f of x is x when x is a rational number, and minus x if x is a non-rational number, then I have to prove that limit x tends to a f of x exists if a is equal to 0. So now there are three possibilities. Either a is a rational number, or a is equal to 0, or a is not a rational number. So now using this, I'll take three cases, in which case 1, when a is a non-zero rational number. Why I am taking non-zero rational number here? Because I have assigned it as a is equal to 0. A is a rational number without 0, and a is a irrational number without 0. So using these three cases, let us try to prove this. So now when a is not equal to a rational number, and it is also a non-zero rational number. So now I'll define the function as the RHL limit, or I'll just define a limit x tends to h tends to 0 f of a minus h. Usually f of x is equal, if I have taken f of x, then my limit is limit x tends to a. Here I will take it as f of a minus h, so I am taking the limit as limit h tends to 0 f of a minus h. So now if I consider my question, this is the question. So using this, I'll write the limit as limit h tends to 0, x will be a minus h. So a minus h. They have given minus x, so minus of a minus h. A minus h if x is rational number, and this is if x is not a rational number. So now if I solve this, if I put limit h tends to 0, obviously both the h will be 0. So I'll get it as a and minus a, which is not unique. So now if I just go on giving the values, I might get 1, minus 1, 1 or minus 1, or 2 or minus 2. So obviously both are not equal. So it is not unique. Therefore, this limit does not exist. So now let us see case 2. My case 2 is if a is equal to 0, then it will be, my function will become f of 0 minus h. So that will be limit h tends to 0, f of 0 minus h. So it will be limit h tends to 0. Since my a is 0, I'll just take minus h and plus h. Why it is minus h and plus h is, first thing, a minus h will give you over here minus h. Here it will be 0, so minus of minus h is plus h. If x is rational and x is irrational, or you can directly take this as minus h, because we have got minus h over here. So now obviously if I put the limit, then my h will become 0. So this limit does exist if limit x tends to a, f of x, if and only if a is equal to 0. So now let us see the third case, when a is irrational. Now, since I have proved it once for rational numbers, I need not prove it for irrational numbers, because I will get the same result. So this is clear that, or we can easily say that f of a minus h is not unique. Therefore, in this also it does not exist. It exists only when a is equal to 0. So overall, if we consider, then the limit h tends to 0, f of x does not exist. This limit will exist if a is equal to 0. So my second example is f of x is equal to x sine 1 by x if x is not equal to 0, and 0 if x is equal to 0. Now let us find the limit x tends to 0, f of x. So now if I substitute the limit directly over here, limit x tends to 0, x sine 1 by x, I can split it as limit x tends to 0 x and into limit x tends to 0 sine 1 by x. So this will be 0, this part. But this will oscillate between minus 1 and plus 1. So now anything into 0 will obviously give you 0. Now the second part, this is when x is not equal to 0. But when x is equal to 0, x is equal to 0, they have directly stated that f of x is equal to 0. So we need not prove for this. Obviously this limit exists and its value is 0 and both are equal. Now let us see the smoothness of a function. Now first let us see the definition of this. A function f from a comma b to real numbers r is said to be smooth on a comma b if derivatives of all orders of f exist and are continuous in a comma b. So now a function f from a comma b to real numbers is said to be smooth on a comma b if derivatives of all orders of f this exist and they are continuous in a comma b, then it is called as a smooth function. Now the symbol for smooth function is of a comma b. This is the symbol. So now let us see the examples for this. Polynomials. Along with this, sin x, cos x, e power x, etc. all these functions are also smooth, or they have a very smooth curve. So now, is this true? We have already studied for Taylor series expansion and all. So now, is it true for Taylor series expansion? Let me just check this out. So now I'll write the Taylor series of e power x. So now if I'll differentiate e power x with respect to x, it will be e power x itself, and e power to 0 is 1. Now if I differentiate e power x n number of times, then I'll get e power x itself. So now the expansion of e power x is 1 plus x square by 2 factorial and x cube by 3 factorial and so on. This is e power 0 and e power x and so on. So now if I represent this, so now if I take x as 1 by t plus or minus 1 by t. So now if I just represent this graphically, then I'll get a graph as at minus 1 by t, obviously e power x will be 0. So this will be a straight line, and at this I'll be getting a smooth curve. But this is not actually a smooth curve because it will be flat after a particular time. So I cannot consider Taylor series expansion as a smooth function. So now let us see the infinitely fixed function. So now let us see what are infinitely flat functions. So now let us define this through lemma. The function f from real numbers to real numbers defined by f of t is equal to e power minus 1 by t if t is greater than 0 and 0 if t is less than or equal to 0 is smooth. So now I'll taken a function f from real numbers to real numbers and I have defined it as f of t is equal to e power minus 1 by t if t is greater than 0 and 0 if t is less than or equal to 0. So now I'll consider this same example of Taylor series. I've taken this representation before itself. So now if I consider this then obviously this is a smooth curve from 0 to the positive side. Whereas when we come to negative side, it is flat. So using this curve, I'll be explaining the remaining part. Now we need to see whether f dash of 0, f double dash of 0, and so all derivatives are 0 or not. Obviously they are equal to 0 when I equate t to 0 because I have defined the function in such a way. So now let us prove this. Here we only need to check that derivatives of all orders exist. At 0. So 1 by t, or in our case we have taken minus 1 by t, is smooth function it outside 0. And so is exponential. Obviously minus 1 by t is smooth when it is outside 0 or t greater than 0, but so the exponential is also a smooth curve. So now here we are trying to show that obviously the function part as well as the t part is continuous, or it's a smooth curve. The only problem over here is origin, because at origin we have considered the function as 0. So now we can prove this by mathematical induction method. So now here we need to show that e power minus 1 by t is a smooth curve. We need not show that t less than or equal to 0 is a smooth curve because it's a constant function. So we did not prove that it is a smooth curve. So now e power minus 1 by t will tend to 0 if t tends to 0. Now this is a well-known property of exponential function. We already know that e power minus 1 by infinity is equal to e power minus infinity. Exponential to the power of infinity is always 0. This is a well-known property. So now the given function f at exponential, f is continuous at x is equal to 0. Now we have to only show that or check whether f is differentiable or not at the origin. Now we need not prove that f is differentiable when t is less than or equal to 0 because it's a obvious case. We have assumed it in such a form. Now we have to only check when t is greater than 0 whether f is differentiable or not. So now I'll differentiate d by dt, e power minus 1 by t. I'll get it as e power minus 1 by t into 1 by t square, which is, so differentiation of minus 1 by t, e power minus 1 by t is e power minus 1 by t into d by dt of e power minus 1 by t. So this will be 1 by t square, which I have written it directly over here. So now we have the claim for t greater than 0. the kth derivative of f is of the form pk of t e power minus 1 by t divided by t power 2k, where pk of t is some polynomial. Now here we have proved that this derivative does exist. So now what I am trying to prove is the derivatives of all the function of f does exist. Assume by assume by inductive hypothesis that the fn of t is pn of t into e power minus 1 by t divided by t power 2n. I have just changed the kth derivative to nth derivative. So now if I have to find out the n minus 1th derivative of f of t, then I'll apply product rule for this first. So pn prime of t into e power minus 1 by t divided by t power 2n plus pn of t into e power minus 1 by t divided by t power 2n the whole prime. So now I'll be concentrating only on this term. In short, I'll be finding the derivative of this term. So now the derivative of this is e power minus 1 by t divided by t power 2n. The whole prime is nothing else but e power minus 1 by t divided by t power 2n plus 2 minus 2n t e power minus 1 by t divided by t power 2 into n plus 1. So now, you guys, if you want, you guys can check this out whether it will give the same derivative or not. So let me just substitute this in this and write the simplified form of f n plus 1 derivative. That will give us t square pn prime of t plus pn of t minus 2n t pn of t into e power minus 1 by t divided by t square. Now we have proved the claim by induction. Now there is another claim. The kth derivative of the function 0 exists and is equal to 0 when k is greater than or equal to 0. That is, now we'll assume again by induction hypothesis the nth derivative of 0 is 0. I'll give the limit t from 0 to 0 plus f of n of t minus the nth derivative of 0 divided by t. So this is nothing else but the limit definition at the origin or at 0. Now this is nothing else but limit t tends to 0 plus f the nth derivative of t divided by t. Now what is this fn of t? It's nothing else but pn of t p power minus 1 by t divided by t power 2n divided by t. This is pk of t times e power, sorry, it's n, e power minus 1 by t. Divided by t power 2n plus 1. So this is nothing else but this part. Now I'll set 1 by t to be equal to some x. Now I'll consider this entire expression as pk of 1 by x into e power x divided by x power 1 by x power 2k plus 1, sorry, 2n plus 1. Now this I can also write it as 1 by x into x to the power of 2n plus 1 divided by e power x. Now this is nothing but limit. I'll apply the limit as x tends to infinity or plus infinity. Now you have already shown that as x tends to infinity, this converges to 0. This we have already studied in continuity and differentiability chapter, which was there for us in second PU. So now this whole term tends to 0. Now since pk of 1 by x is a polynomial, so it goes to a fixed constant. Now anything into 0 will give you 0, so the whole term converges to 0. So in short, this means that the right hand derivative of all orders of f exists and is 0. In short, this means that the function f is smooth. So now we have proved that the function f is smooth, and this is for the exponential function of the Taylor series where we have taken x as minus 1 by t. So now let us go through the derivation once again. The lemma states that the function f from real numbers to real numbers defined by f of t, where f of t, I'll define it as exponential function as e power minus 1 by t. If t is greater than 0 and if t is less than or equal to 0, then the function will go to 0. Now we have to just prove that this is smooth. In short, we have to show that all the derivatives are equal to 0. So we'll do this by mathematical induction method. Now we already know that the function is a smooth function when it is outside of 0. And so is the exponential function. So now the given function, we have also proved that the given function is continuous at x is equal to 0. So now when t is less than or 0 equal to 0, then obviously it is an obvious case because we have taken it as 0. So all the derivatives will obviously equal to 0. But when t is greater than 0, we have to just show that the derivatives are 0. So now if I derive this e power minus 1 by t, I will get it as e power minus 1 by t into 1 by t square. Now we will prove this by induction hypothesis. For this we have taken the kth derivative pk of t into e power minus 1 by t by t power 2k, where I have considered a pk of t as some polynomial. So now by inductive hypothesis, we have shown that this is true. We have proved the claim by induction hypothesis, where I have derived the Pn of t, the nth derivative or the kth derivative, which I have considered as the nth derivative. We have proved it for n plus 1th derivative also. Now we have to just check whether this fk of 0 exists and is equal to 0 or not. So again by induction, we'll take fn of 0 is equal to 0. I have taken the limit at the origin because I have taken as x as 0 and I have got as 0. So I have taken it as the limit at the origin, and at the end I have got the result as 0. So obviously the right hand derivative of all orders of f exist and those all are 0. Therefore the function is smooth. Thank you for watching the video.